Okay. So Ali reminded me that I should record, which I didn't. Okay, so again, what are we going to do today? We're going to do a new algorithm called merge sort. It's a recursive algorithm. So it takes an input sorted list, and its goal is to return the list sorted at the end, an ascending order from smallest to largest. So how does it work? You take the input list, which is unsorted, and you split it in the middle, so into two sublists, each of roughly half of the size of the input list. Then you do the same recursively. You take the first half, you split it into two halves. Yeah, you take the second half and you split it into two halves. Great, okay. And you keep doing this. So we take, now this quarter and split it into 1/8, the original size, and so on. Keep doing this until you get a sublist of only one element. So that's the base case. When you had, one element, you have multiple of these guys. Each one is just a single element. Now, the idea is that if I have a list of one element, it's sorted. Yeah. So once I hit the base case, which is a list of one element, the input to the function, this merge sort has a list of one element. That means the list is sorted and I can return. So what I do is now I have, two sublists that are sorted. I merge them in the right order, and we'll see the algorithm for merging in a bit. Yeah. So I have initially I would have hit the base case for a single element of the list, each one of them, and I'm going to merge these so that they are in the correct order. Yeah. And that will give me, sorted sublists. So I go back bottom up, merge these guys, merge these sorted sublists to get, larger sorted sublists. I keep merging until I have, two halves. Each is sorted on its own. Merge them, I get the list sorted. Yeah? So it's really cool algorithm. Of course, we need to fill in the details. How do I do the merging, basically? All right. So let's see how this works. Let's start with a video. We'll see it live with MIT students, like I think the selection sort, we've seen a demo of that. And then.
So we're about to demonstrate merge sort, and we're going to sort this rather motley collection of MIT students by height. So the first thing we need to do is we're going to ask everyone to split into a group of two. So you split a little bit. You two are together. You two are together. You two are together. You two are together. And you are all by yourself. I'm sorry. All right. So now let's take the first group, take a step down. And what we do is we sort this group by height with the shortest on the left. And look at this, we don't have to do anything. Thank you. Feel free to go back up. We then sort the next pair, please. And it looks to me like we need to switch. All right, take a step back. Ladies. Okay. Ladies, gentlemen. Also okay. And again, okay. And I think you're in the correct order. Now what we do is we take these groups and merge the groups. So let's have these two, going to sort these groups, have them step forward. And now what we're doing is we're doing a merge of the two sorted groups. So we start by merging them. We'll take the leftmost person in this group and compare her to the first person in this group and decide she's still the shortest. Take a step back. Now, we're going to look at you and say, you're actually taller than this fellow. So you now step up there. And we're good here. Both of you take a step back. Now we'll take these two groups and follow the same procedure. We'll merge them. Let's see, we'll compare you the first person in this group to the first person in this group, now it's a little tricky. So let's see the two of you compare. Let's see, back to back. We have a winner. Step back. And now you need to compare the shortest person in this group to the shortest person in this group. We have a winner. It's you. I'm sorry. And now we're okay. Please step back. Now we'll have these two groups come forward. We'll compare the shortest person in this group to the shortest person in that group. I actually need you guys to get back to back here. You are the winner. And it's pretty clear that the shortest person in this group is shorter than the shortest person in that group. So you go there and you step back. And now we repeat the same process. And you can see that we have a group of students sorted in order by height.
All right. So this was a demonstration using, real students from MIT. Let's see another example with numbers. Okay. How many were they? They were, I think, let's see, I don't know.
So we're about to demonstrate.
2, 4, 6, 8, 11. Okay. Yes, Chad, you want to ask another question? You raised your hand. Okay, good. So let's see an example with numbers. I have a list. Okay. I have a list here. Right? That's the input list. It's unsorted, obviously. And I want to sort it using merge sort. So the first step is to split roughly in the middle. So figure out what is the middle of this list in terms of indices, and roughly split into two sublists, each unsorted on its own. So all I did, right, was take these guys until 9, that's the first half, and then from 7 till 3, that's the second half. Didn't do any sorting. Then I'm going to recursively repeat the same thing. 8, 2, and 4 becomes, 1 half or 1 quarter, and 6, 9, the other quarter. Same thing for the other half. 7, 10, 1, and 5, 3. Okay. And when do I stop splitting? Once I hit one element only. A list was one element. So here 8, 2, and 4, I'm going to say, okay, half of the list, the first half is 8, 2, and the second half is 4. And then, right, for 6 and 9, it's two sublists, each with one element, so I can stop splitting and so on. Yeah, so I'll keep doing this until I have a single element. Okay, now what do I do? From these single elements, I'm going to merge in the right order until I get the full sorted list. So I have 8 and 2. How do I merge them in the right order? 2 should come before 8. So I'm going to compare this element. You know what? It's an algorithm. So the merge is an algorithm that takes two lists, each sorted, and give me one list containing both of them in the right order. So I'm going to compare 8 and 2. 8 is smaller, so I'm going to put 2 first. Sorry, 2 is smaller, so I'm going to put 2 first and then 8. And now I have this list merged, sorted, and now I need to merge it with 4. How do I do this? I compare the first element here with the first element in the second list. 2 and 4, which is smaller, it's 2, so I'm going to put it first. And then 4 and 8, I'm going to compare them. 4 is smaller, so I'm going to put 4 first. And then finally, I have just 8, so I'm going to put it. So now you're seeing that as we're merging these lists, right? We're getting larger sorted lists. Same thing for 6 and 9. We're going to be merged into 6 and 9. 7 and 10, they're in the right order, so they're going to be merged. And then I have to merge 7, 10, and 1. It becomes 1, 7, 10. 5 and 3 will end up being 3 and 5. Okay. And now I have to merge 2, 4, 8, and 6 and 9. How do I merge 2, 4, 8, and 6 and 9? It should be 2, 4, 6, 8, 9. Okay, so I get this sublist. Now I have 1, 7, 10, and 3 and 5. How do I merge them? I compare the first element here with the first element here. Okay, 1 is smaller than 3, so 1 gets pushed in the output list first. Then I have 3 and 7. 3 comes next. Then I have 5 and 7. 5 comes next. And now since this list is empty, I'm going to now push the 7 and 10. And now I have two halves that are each sorted on its own. All I have to do is merge them. Again, I will compare the first element here with the first element here. 1 is smaller, so I put 1. Then I have 2 and 3. 2 is smaller, so I'm going to push 2. And then I have 3 and 4. 3 is smaller, so I'm going to push 3. And so on until I get the list completely sorted. Questions about how the algorithm works, the intuition behind it, before we get into the code. Any questions? So again, the idea is split half, 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 half recursively till you hit the base case, which is a list of one element. You stop splitting and you start merging. Yeah, merge lists so that they end up being sorted once they are merged. Questions? All right, let's see. First of all, how does merging works before we get into the code? So let's assume I need to write a function that takes two lists, each sorted, and merge them in the right order. So I have the first list is 2, 3, 5, 6, and the second list is 1, 4. Okay. So what do? I compare 1 to 2, the first element in the first list with the first element in the second list. So 1 is smaller than 2. I'm going to push 1 into the output list or the merged list. Okay, and now I have 4 in the second list because I pushed 1. I got rid of 1. And I have 2, 3, 5, 6. I'm going to compare 2 to 4. Since 2 is smaller, I'm going to put it as the second element in the merged list. And now I have 3, 5, 6, and 4. I'm going to compare 3 to 4, the beginning of this list to the beginning of this list. That gives me 3. And then I have 4 and 5 and 6. So 4 is smaller, so I'm going to push 4. And now since this list is empty, yeah, so it doesn't have any elements, I can push all the other elements in the other list because we know that they are all greater than what I've seen so far. Okay? So let's see the code. So the code looks like this. First, I'm writing the code for the function merge. Merge takes as input two lists, each sorted on its own, and I need to merge them in the right order. Okay, so I have this merge. That's going to be the list, the output list. That is the result of merging these two lists, L1 and L2. And what I'm doing is I'm looping. You know, as long as neither of these lists are empty, or I haven't been done reading all the elements in both lists, I need to compare the first element of the first list with the second element of the first element of the second list. So I'm looping as long as I starts with 0, J starts with 0. So I'm starting at the beginning of both lists, and I'm saying, okay, compare the first element from L1 with the first element from L2. That's this comparison. And if the first element in L1 is smaller, append it to merged and increment I. So move to the second element of the first list. So keep J in its position. And if it's the opposite, I'm going to keep I in its position at the first element because L1 of I was greater, and push the first element of the second list and move J by 1. Okay, so this is the code doing the thing we just did in the table. So look at the first two, the two lists, and then decide which one to move into. Okay. And once you're done, so once you exit this loop, I exit this loop because either I has been greater than or equal to length of L1, or J is equal to length of L2. So meaning what? That I finished one of the lists, at least one of the lists. Okay. Now what do? I just extend, whatever is left in in both lists. Of course, one of them would be nothing. So because I finished reading all the elements there, so there would be no elements to extend. And depending on which one I finished, all the elements there will be added to the merged list. Okay, so that's really just the merging code. Of course, you can write it in various ways. This is just one possible way of writing the code to do the merging. Questions? Check the code and let me know if you have any issues with any of them. So far, so good? Okay. Good. So now, oops, sorry. What is, first of all, we'll discuss the complexity of the previous algorithm, and then we'll go to write the whole merge sort algorithm. So the main function, the recursive function. So this algorithm, what do you think its complexity is in terms of the input, which is the size of the two lists? Any thoughts? How many times does this loop run? In the worst case, maximum number of times this loop would run. That's really the most expensive operation. When do I exit this loop? Again, this loop is doing what? Going over these two lists in parallel, and it only stops once I finish the one of the lists. So minimum or maximum? Mariam is saying the minimum of length of L1 and L2. Okay, let's see. It's really in the order. It doesn't matter if it's minimum or maximum. It's in the order of length of L1 plus length of L2, right? Why? Because I don't know exactly which list is going to end first. It depends on the size, on the elements. Yeah, it might be that list 1 has more elements than list 2, but list 2 has more things. So it's just the order of these guys. Yeah. So it's really, in the worst case, I'll go through the longer list. That's the worst case. Yeah. So it's not minimum, it's maximum. Why? Because I'm looking at the worst case. Yeah. It could be that in one case it's minimum, right? The minimum of the two lists, but in the worst case, I will have to go maximum through the larger list, and then I'm done. Because once I finish the larger list, I inserted all the entries of the list, then I would have the other list left to do. Wouldn't the loop end when the shorter list is done? Not the shorter list. Let's say I have the following. Yeah, I have here 1, 2. Let me see how do I put it correctly. Okay, so I have 1, 2 here, and 3 and 4, and 5 and 6. Okay, so which one is the shortest list? The second one, this one. But I will have to loop at least 4 times before I exit this loop. Why? Because I'm going to compare 1 to 5. Oh, 1 is smaller, so add 1. Then I'm going to do 2. Is 2 greater than 5? No, so I'm going to add 2. And then 3. So I'm going to add 3. And then 4 is smaller than 5, so I'm going to add 4. And now this list is completely done, and I can just exit the loop. Do you see it now? That's actually the maximum, or the longer, not the shorter. Is just a complete example, illustrative example. Mariam and Rawad, do you see it now? Great. So then it's really the big O of the maximum of length of L1 and L2, yeah, which is big O of the length of the list. Yeah. Okay. Let's see the merge sort code itself. So I have now the merge sort is supposed to take an unsorted list, one list, and then it returns at the end the list sort. Okay. So it's a recursive algorithm, so I'm going to write it in this way. If length of L, that's the base case. So this is the base case. So what is it? What is the base case that we have? If my L is less than two elements, so it's one element or an empty list, it's sorted. Just return the list. And here I'm doing a copy of the list, yeah, just to not change the list itself. Yeah, so I'm returning a copy of the list. By doing this, you know, I'm cloning the list. Okay. Now, if the list has more elements than two, what I'm going to do is find the middle element. That's how the algorithm works. So split in the middle, do merge sort of the first half. So call yourself recursively with just the first half of the list from L till middle. So right before the middle element, and then the other half would be from the middle element all the way till the end. That's the second recursive call. And then once you're done with any of these recursive calls, merge, you know, these sublists. So I will stop doing these recursive calls once I have a single element. And all I have to do is merge the, you know, two elements to get, you know, a sorted list, and then merge the sublist with the other sublist, and so on. Yeah. So really split in the half. Call yourself once on the first half. Call yourself once on the right half, and once you're done, merge the two sorted sublists using this algorithm, this function. Okay. Let's see it in action. So I'm going to show you how it works with the recursion, with everything in action. Okay, so I have this input. So 8416592. First step is figure out what is the middle. So figure out the index of the middle. How? By just dividing the length of the list by 2. Okay. So I'm going to call myself again on the first half, because I'm doing this. If you look at the code, doing middle, you know, call myself on the first half, call myself on the second half. So I'm going to figure out what is the middle, call myself on 8416. Okay, that will, you know, result in another execution of the same function. Get the middle, call yourself on 8, the first half. Yeah, because I do this first. If you look at the code, I do this, and then I say left is equal to merge sort of the first half, and that will go back and call the function before I can, you know, execute these two lines. I will have to go back, call myself, I'll go through this code, keep doing this until I hit the base case. That will allow me to move to this state. Okay. So again, half, that's 8416, half, that's 84, half, that's 8. So I hit the base case. That's the first time I hit the base case. So I'm going to return this value. Since it's one element, yeah, that if you remember the base case, it says if you know the list has less than 2 elements, just return a copy of the list. So it's going to return 8 to the caller. Now I can go to the next line, which is, you know, right is equal to merge sort from middle to the end. That's in this case 4. That's another base case. I'm going to return 4. And now I finished, you know, these two lines. You know, left is equal to merge sort from the beginning till the middle, and right is equal to merge sort from the middle till the end. Now all I have to do is call the merge function on the returned elements, returned list 4 and 8. So that's going to merge and give me 4 and 8. Okay, now I return this to the caller, yeah, because now the function, the method finished, and I would be returning this value to the caller. Okay, now 4 and 8 is going to be returned, so I can move to the next line, which is merge sort the other half. So 1 6, that's going to call, you know, 1 base case, return the 1, 6 also base case, return the 1, then merge. So I get 1 6. That would be returned to the caller. Now I have to sublist each sorted, merge them. That will give me 1 4 6 8. Okay. Now I can return this to the caller and move to the next line, which is sorting the other half, the second half. So 5 9 2 0. Again, I split in half. 5 and 9, that will go split in half. Base case, return the 5. 9, base case, return the 9. Merge, we get 5 and 9. Now return this 5 and 9 to the caller. Do the second recursive call on 2 and 0. Split, base case, return, base case, return, merge 0 and 2, merge 0 and 2, 5 and 9. That gives me 0, 2, 5, 9. Right, so 0, 2, 5, 9. And now I have, I'm going to return this to the caller, and now I have two sublists. One is 1468, and the other is 0, 2, 5, 9. Merge them. Using the merge algorithm, I get all the elements sorted. Okay. Get it? Okay. So what is the complexity of the algorithm? Let's see. So if you look at the algorithm, right, I have a whole list. The first recursion, what will happen is I'm going to split the list into two halves. So if I had n elements, the list had n elements, it become n over 2 elements in each sublist. Okay. So why is it big O of n plus big O of n? Because really I'm doing the merge. Yeah. So the merge of the first half would be basically big O of n. Yeah. I'll show you them, but let's go through the slide and then I'll show you what this means. Okay. So at the second recursion level, I have now four quarters. Each has n over 4 elements, but I'm doing 2 merges. Yeah. So each one is big O of n. Each of the merges. I have n over 2 elements, n over 4 elements, n over 4 elements. That's big O of n. Okay. And each recursion level, I increase the number of sublists that I have to merge, but I decrease the size of each sublist. So it's every level I have n big O of n or big O of length of L, the operations. Now dividing the list in half, how many of these do I do? Right, that's big O of log n. So I have big O of log n merges, which is the log n times n. Yeah, so this algorithm is n. Okay, let's see what this means. Okay, I'm going to try to do this again with you. Okay, so I had originally n elements. I'm going to split into half. Let's focus first on the number of recursive calls. Yeah. So this is really log n. Why? Because I split in half, then split in half, then split in half until I hit one element. We know this successive splitting in half is log n from binary search and from previous things that we've done on complexity. I have n elements. Each time I'm splitting it. Now, what happens in each one of these? I'm doing here. How many merges? That's 1, 2, 3, 4, each of the size 1. So I'm doing log n. Each one is, of course, big O of 1, big O of n, right? Where n is the size of the current sublist. So in total, I have to go over all the elements here to merge. Exactly, Jack. Yeah. And then I do the same thing over here. Yeah. Now I have these 4 sublists, each of 2 elements, but I have to merge, these guys alone, these guys alone. That's gonna eventually lead to big O of n. Yes, Jack, it's exactly n log n. Then I have this and this. Each one is n over 2, but we know that, the merging of them would be big O of n. And so I get at the end. Each one of these merging, although I'm doing merging of small lists, but I'm doing them multiple times. So at the end, it's really big O of n. So the whole algorithm is, how many times do I do this recursion times, what time, how much it takes per recursive call. Yeah, per recursive call, I really, or per level of recursion, I'm doing log n, sorry, big O of n merges or operations in the merge. Okay. So this algorithm is in total n log n. Just need you to know the intuition. There is various ways of analyzing recursion or recursive algorithms. We haven't covered them. You're going to see them in 211 if you're continuing with computer science or you're a computer science major. You're going to see them in discrete mathematics and also in 256, the algorithms. So there's something called recurrence relations that we're supposed to write. So this is just an intuitive analysis of the algorithm. Yeah, nothing that is mathematically very deep or sound. There's a better method that is absolutely mathematically derived, and you're going to see it in other courses. Just know that the intuition, and know that merge sort is really the fastest sorting algorithm out there. So to summarize, for sorting, we have insertion sort is big O of n squared. Selection sort is also big O of n squared. We analyzed them. They have both of them have two nested loops. So basically, each one run a maximum of n, where n is the size of the list. The merge sort, as we've seen, is n log n, which is faster definitely than n squared, especially as n grows. Yeah, and this is the basically the upper bound, the lower bound on how fast the sorting algorithm can be. So you cannot get any sorting algorithm that's going to do better than n log n if it's a deterministic algorithm. All right, now I think you can implement the merge sort exercise in the assignment. Go ahead and do that. This code is also uploaded on Moodle, and you can definitely work on the next exercise, which is using the merge sort to sort a list of fractions. So I think that's the more interesting exercise there, because this you have the code for it already. Questions? Okay. So that ends all the material for the course. Now I'd like to spend the 10 minutes remaining working on discussing a little bit the exercise on the palindromes, if you have no questions about this. Okay. It's not greater, Jad, right? N log n is smaller. So that's why this merge sort is faster. Right? A faster algorithm means I have less number of operations. So I ideally want the number of operations to be as small as possible. So we're saying sorting, the merge sort has n log n, and that's a smaller value than n squared. Yeah. For any n positive integer, always have n log n is going to be smaller than n squared, because log n is less than n, correct? Okay. And that's why it's a faster algorithm. I always want this bound, the big O, to be smaller, not larger. Okay. All right. So let's go to the palindrome exercise. Where do I have it? Yeah. So there were two exercises on the palindrome. Again, I want to find the length of the longest palindrome inside a string. Last time we discussed the brute force algorithm. And what it does is it goes over, generates all possible substrings, and then measure, figure out if it is a palindrome or not for each possible substring. And if it is a palindrome, it records its length, and at the end, figure out what is the maximum length and the corresponding palindrome. Yeah, so we discussed this the last time. I'm not gonna repeat it, but let's analyze its complexity before we move to the second algorithm. So can somebody look at this code, right, and tell me what is the complexity of this function? Longest palindrome. Even without really knowing what it's doing, I can always tell what is its complexity. big O of n squared, okay, where n is the length of the string. That's okay, but it's not exactly right. Why? So that there are two nested loops and each one is n, so it's n squared, but I have the palindrome function as well. The palindrome function is taking time. It's an expensive operation. It's not a constant. Yeah, I don't pass a string to the function palindrome and it does a constant number of operations. It does something that depends on the length of the substring, which maximum can be the size of the whole string. Okay, so what is the palindrome function? What do you think is? I know it's recursive, but so there is no loop per se, but how many operations happen? If I give it, how does it work? It takes a string, let's say, something like ABBA. And how does it find out whether this is a palindrome or not? It checks this guy with this guy. And if it is, the same, it moves to the next character and the next character and keep repeating this until it, either finishes or you find the two characters that are not the same. So in the worst case, what is the complexity of this function? It's big O of. If I give you a string like this, A, B, C, A, B, C, right? We'll have to go do 3 comparisons. Yeah. If I give you X, Y, Z, W, X, Y, Z, right? It will have to also do roughly, n over 2 comparisons, where n is the length of the substring. Yeah, so I have to compare this to this, this to this, this to this, and then there is a single character. So overall, right, this also is a big O of n, where n is the length of the substring. Why big O of n? Because I'm doing worst case, so I want to see the maximum number of comparisons that happen here or operations that happen here, and it depends on the size of the substring, and the maximum value the substring can have is actually the whole string. That I could look at the whole string. All right, and then I ignore constants, so n over 2 versus n doesn't matter. Big O of n over 2 is the same as big O of n. It's a constant. Half is a constant. Okay, so overall, it's big O of n cubed. The n squared from here plus this guy, which is big O of n. If you multiply this, you get big O of n cubed. And we've discussed that n cubed is really a very bad one. Okay, now let's see the other one. Clear. We can repeat this on Wednesday. Okay. Okay. So here's the method that does this trick. Looks at generating even and odd palindromes, and it works this way. I'm going to loop over every character in the string. Let's say I have the following example. I have 2 strings. One is, X, ABBA, okay, and then Z, for instance. Okay, so let's start with this example, right? So I have an even palindrome. So the longest palindrome in the string is actually ABBA, and it has a length of 4. Okay, so I'm going to loop over every element inside the string, and I try to generate around it try to find out palindromes around this character. There are 2 cases. I could have a palindrome that is of odd length, like ABBA. Let's say I didn't start with X, I started somewhere here, because I'm doing this over every character inside that string. So let's say I am at this position B. I want to find if there is a palindrome around B. Yeah, there are 2 cases, either a palindrome of odd length or a palindrome of even length. If I'm looking at a palindrome with even length, right, then I need to check if this character is the same as the previous character. Right? So let's say I was here instead of here. And so I'm gonna just erase here something. So assume I was here. Yeah. And now I want to check if this character is the same as this character. So for even palindromes, I want to check the character and its next. Are they the same or not? Okay. And then if they are the same, I move to this guy. Where's the pen? How do I get back to the pen? Mouse, maybe? Yeah. Okay. No. No. Maybe. Yeah. Okay, fine. So I'm gonna move. Sorry. Let me just do this. Text. Where is it? Where's the pen? Oh, let's try this. Okay, fine. Okay, so now I check B and B, they're the same. So I'm going to move to this guy and this guy. And I keep doing this until I hit, two letters that are not the same, like here, X and Z. That's for the even case. For the odd case, I have the following. So let's say I have the following palindrome. So I'm going to do this, then annotate. Then let's say X, A, B, C, A, B, and then Z. So what is the longest palindrome here? It's again this guy. Yeah, A, B, C, A, B of length 5. Because you can read it from left, same as right. So now let's assume I'm at C. So what I'm going to do is I want to check the previous character with the next character. Right? So it should be BA, right? So I'm going to check this character with this character, did the same, yes. Move to this guy and this guy, and keep doing this until you hit two different characters. So there are these two special cases, one for even and one for odd. Okay. So now I'm going to repeat this for every single character inside the string. So for every single character inside the string, that's this loop. Do expand and count how many characters you've expanded, once for the odd and once for the even. So for the even, it's, you're giving it the start and the end is the same. Yeah. So why? Because I'm gonna say, okay, start from the beginning and from the end and check whether the start is equal to the end. So I want them to be the exact same index. Yeah. So that's, I look at the character in the middle for even and then decrement and increment. So go to the previous character and the next character. Okay. And for the odd case, I want to really look at, the character to have them different. So this is I and this is I plus 1. To have, look at this character and sorry, that's the even case. So ABBA, I want, B. So that's position I and the next B, which is I plus 1. For the odd, I want them to look at, the same character and then move to, the previous character and the next. Just in a nutshell. Okay. And that's it. And then you get back, you stop this loop once you have hit two different characters at the current start and end, and you return this palindrome, you check its length. First of all, you check, because I'm looking for every character at the even palindromes and the odd palindromes, so check which one is larger, keep it as the longer, then check if this is the longest you've seen so far. That's it. I can repeat it again on Friday because we're running, on Wednesday because we're running out of time. So we can start with it and then take questions in general in the class. If you still have questions about this, I'm also going to stay a bit online. So you can leave now, or if you have questions, ask, or, it's up to you. But I'll stop recording at this moment. Okay.